So I'm going to be talking about the physiology of fitness and the acute responses to exercise. So acute exercise, this is going to be looking at the response to the first few minutes of exercise, like when you jump on the treadmill or when you warm up, and many other sport situations that I'm going to be bringing in this presentation. Is going to be split up into the musculoskeletal system responses, the energy systems responses, the cardiovascular systems responses, and the respiratory systems responses. So the first one, the musculoskeletal responses to acute exercise, it increases the blood pressure. So just before we start exercise, we just warm up. So the body detects sudden movements in the body, which causes the heart to pump faster, which increases the blood pressure and increases the blood supply. This is so that the muscles are provided the right amount of oxygen and glycogen that the blood has inside it. During exercise, many things happen to the skeletal system and the skeletal muscles. One of them is the increased demand of oxygen and glycogen. Also, the blood supply changes. At rest, there's 20% to the skeletal muscles. At warm-up, there's 50%, and at the exercise, it's 80%. This is all that, so the cardiac muscle, which is the heart, can provide enough oxygen and glycogen, plus to get rid of the waste products, for example, carbon dioxide, water, and heat. Also, the cardiac muscle beats much faster, and with a larger amount of blood going through each beat. The blood is shunted away from parts of the body that don't need it. For example, the stomach, when we start exercising, it's 1%, however at rest it's 25%. Sporting example, so let's say Ronaldo, he does his warm-up, his heart will start to beat faster to make for the oxygen that is lost and glycogen, and to get rid of the waste products. This is all done by the blood, which is why it's transported faster to the muscles to allow Ronaldo to have enough nutrients in his muscles to last the whole game. The next bit is increased muscle pliability. The main point of more warm-up is to increase the pliability of the muscles, so the stretchiness. This is because the body's temperature is increasing, causing the muscle tissue becoming warmer, as well as just become warmer, which is why it's called a warm-up. The warmer the muscle, the more pliable it is, so it's more stretchy. This makes the muscle less prone to micro tears. It's caused by the exercise, which reduces the cramps and increases the performance of the player. This also causes the muscle to be more elastic and have a better range of movement. An example is, for example, a basketball player. He starts to warm up just before the game. This allows the muscle temperature to increase, which makes it more pliable, more stretchy, and less likely to tear. So when he runs or goes for a shot, he can stretch. For example, he's going for a shot, he can stretch the tricep further, which makes him increase in performance. Another response is the increase in range of movement. This is done within the first few minutes of exercise or in warm-up. The body responds by producing more synovial fluid at all the joints, and it is thinner, warmer, increases the efficiency of the movement. Synovial fluid increases the range of movement at the joints because it lubricates them, allowing less friction to occur. This makes us move faster, as the friction between the bones is not stopping the range of movement and the joints from producing any movement. An example is a rugby player. He's warming up, he's putting more stress on his joints. This causes the body to make more synovial fluid to allow him to carry on making these movements. Due to the increase in intensity, as the game goes on, it will carry on doing this until it's smooth enough. And lastly, there's the muscle fiber micro tears. So when we do exercise, the muscles fibers they tear because of contraction. This means that the contractions are stronger because there are more fibers that are used for contraction. In the short term, muscles are damaged by the exercise, which is caused by micro tears, which are small tears in the muscles. This is why we feel sore after exercise. So only with the appropriate food and rest will the micro tears be able to eventually repair stronger. An example, let's say a football player, he's playing a football game at the beginning. Every time he plays football, depending on obviously the intensity and how hard he works, the muscle fibers will tear, and his legs will mostly, the micro tears will mostly appear in his legs. Then after he rests and eats, the fibers will repair stronger. than before, making him better at the sport. And another example is when my college, we did a run, a 6-minute run in the gym. We did 20 seconds of sprint and then 10-second rest. But before that, we did a warm-up. And when we did this, we recognized that our muscles were really hurting after this exercise. This is because of the micro tears and all of the other things were happening, like range of movement was increasing after the warm-up. The muscle was more pliable because of the warm-up, and increase in blood supply as there were less oxygen and more carbon dioxide. So the next bit is the energy systems responses. So the energy systems are the phosphoprotein, lactic acid, and aerobic energy system. These are all different systems and all used at the beginning of the body exercise. Phosphoprotein, this approximately lasts for 6 seconds, and it's normally used for high intensity. This is an example, is a 100-meter sprint. Lactic acid, it starts after 10 seconds. This approximately lasts 1 to 3 minutes, and it's for medium intensity and medium duration. For example, a 400-meter sprint or 800-meter sprint. An aerobic system, this happens after 1 to 3 minutes. This can go on literally for hours. And an example is a marathon or 1,000 or 1,500-meter sprint. Run. And of course, all of this will depend on the fitness of the player and, for example, the lactate threshold. So this is how early the lactic acid system comes in place. The fitter you are, the more it is prolonged and the more it is procrastinated. And this is a diagram showing how much energy is produced and for how long. So obviously ATP is first, then creatine phosphate, then the aerobic system. So the next bit is energy continuum. This is the interaction between all three energy systems in the body to produce the maximum amount of energy supply demanded from the muscles. These are like taxi, because one supplies the energy and the others are able to resynthesize. Here's a diagram again, showing the percentage of energy used from each of the systems and how the performance level decreases over time. Of course, it will vary depending on the intensity and the fitness of the player and the duration. So the overall performance will decrease. They're all fluctuating because some have to resynthesize, some have to produce the energy. So the next bit are the requirements of different sports and exercise. So remember that all three energy systems contribute at the beginning of exercise, but the contribution depends on the individual, the effort applied, and the rate at which the energy is used. So here's a picture, here's a diagram showing all the different requirements needed by each different sport. For example, archery, this requires a high CP system, creatine phosphate, because it's not a very long duration and it's very intense, as the person who's with the ball has to only be there for a few seconds, and you can look at the rest. The cardiovascular system's responses, one way is the heart rate anticipatory response. Though normal resting heart rate is 60 to 80 beats per minute, however, pre-exercise, the heart rate usually increases above the normal resting values. This is due to anticipatory rise, which is your brain realizing what you're about to do and responds by making the heart beat faster by the nervous system. This is not a reliable estimate of the resting heart rate. This is because it has to be, the heart rate has to be recorded a bit of time before the actual exercise. This is due to the sympathetic nervous system, the SNS, releasing adrenaline, which is a hormone in the adrenal glands that increases the rate of the blood circulation, the breathing, and the carbohydrate metabolism, and prepares muscles for exertion. A typical example is a player making his debut for a top team. For example, let's say Zlatan Ibrahimovic, his first game for Ajax, his debut, his heart will be pumping really, really fast, and lots of adrenaline will be released because he's nervous. This normally happens when you're nervous. And there's activity responses. This is similar to anticipatory response. At the start of exercise, the brain, which is the medulla, detects the decrease in oxygen and increase in carbon dioxide. This then sends a signal to the heart to beat faster and stronger. So it releases more blood with each beat. This means that the oxygen is transported to the muscles at a faster rate. As you approach the point of exhaustion, your heart rate starts to level off or plateaus, as people say, and it's because your heart rate is at its maximum. An example, let's say a basketball player, he starts to play at the beginning, or he starts to warm up. His activity response will be for the brain, the medulla, sending a signal to the heart to be faster and stronger, as a decrease in oxygen and increase in carbon dioxide. Hence the diagram showing how the heart increases and how much oxygen is taken up with each minute. Then there's an increase in blood pressure. Again, the resting heart rate is 60 to 80 beats per minute. However, it will increase at exercise. This is done by the systolic blood pressure, the SBP, which is 110 to 140 millimeters Hg at rest and can be over 200 millimeters Hg after exercise. And then there's a diastolic blood pressure, DBP, which is 60 to 90 millimeters Hg at rest. However, it could increase up more than 15 more millimeters Hg as exercise intensity increases, and can indicate that you have coronary heart disease. The SBP, which is the systolic blood pressure, is at its highest, is the highest pressure with the bloodstream, and increases the direct proportion to the increase in exercise and intensity. And as exercise begins, the baroreceptors, which detect the change in blood pressure, which are found in the aortic and aortic arteries, detect a decrease in blood pressure, and specifically the SBP. The DPP, which is the diastolic blood pressure, is the lowest pressure within the bloodstream and does not change significantly, may even decrease. This all causes an increase in the blood flow to catch up with the demand of oxygen and get rid of carbon dioxide. An example is a football player, let's say Wayne Rooney. He warms up, and just as he starts playing the first few minutes, his blood pressure will increase significantly. This is because the baroreceptors are there, and they recognize the change in blood pressure. They need more oxygen, they have to get rid of more carbon dioxide because it's building up. So it sends a signal to the heart to beat faster, and more blood goes through each beat. Then there's vasoconstriction and vasodilation. Vasodilation is basically when the blood vessels widen to increase blood flow, and vasodilation, vasoconstriction is narrowing the blood vessels to decrease blood flow. So basically, let's say they're in a really cold place, a football team are in a really cold place. Vasodilation will happen, vasoconstriction will, to allow the body's temperature to increase. And then during exercise, body temperature rises in order to disperse the heat, blood vessels, and expand, which is vasodilate, and move towards the surface, so this, it can release more heat. Blood being directed away from certain areas, shunting. Example, the organs that don't need it will be redirected towards the to the muscles, and the blood vessels that are going to the organs will vasoconstrict, so they get smaller, so that the blood goes to the muscles more. As we start to exercise, the blood is shunted away from the organs that we don't need, as I said before. An example is the stomach. 25% of the blood goes to the stomach at rest, however at exercise it's 1%. And here are diagrams showing, for example, the sphincters, they stop the blood going through here, so that it can go to the muscles faster, because it's only going through one way. The sphincters allow this. And here's a diagram showing the amount of blood given to the skin, the muscle, the heart, the brain, and all the organs, and how it changes at exercise. So one example is, let's say a tennis player, he's warming up, he just starts to play, the blood flow changes to react to the muscles' demand of oxygen and the accumulation of carbon dioxide has to get rid of. Other than all the other ways of helping the body, it will also vasodilate the blood vessels going to the muscles and vasoconstrict the muscles. The blood vessels going to the organs, like the stomach. Then there's respiratory systems responses. There's neural and chemical control. When exercising, the breathing rate increases, which is detected by the neural and chemical control of the body. The stretch receptors in the lungs detect increased rate and depth of breathing. The respiratory centers, the medulla and the pons, send nerve impulses to the respiratory muscles that control the breathing frequency and tidal volume of each breath. The respiratory center are responding to the central nervous system and peripheral nervous system information. Other information comes from chemoreceptors and mechanoreceptors in joints and tendons and active muscles that assess movement and metabolic status. So one way is increase in breathing rate. Breathing involves two things, inhalation and expiration, which is an active process. Just before exercise, there's a tiny increase in breathing known as the anticipatory rise, which I said before, which is the brain realizing what you're about to do. So you have to breathe faster. It's because we're nervous mostly. When we exercise, the breathing rate at the beginning increases significantly. This is because of the receptors working with both muscles and joints. The muscles demand for oxygen changes, and the carbon dioxide increases due to the increase in energy production. Therefore, an increase in breathing rate is done to satisfy the demand and get rid of the carbon dioxide. And then there's a capillary network surrounding the alveoli expands, which results in increased blood flow to lungs and increased pulmonary diffusion. Here's a diagram showing how the oxygen consumption starts to plateau over here. So if the intensity continues, the breathing will plateau. When athlete reaches the maximum level of carbon dioxide of oxygen consumption, and then it will normally go down here if the intensity is the same. An example, let's say Ronaldo, he's sprinting for a through ball, and then 30 seconds run after that. When he stops, what will happen? Here's a diagram showing what will happen. The frequency at resting is normally 12 to 15, however after exercise it's up to 60. Then there's expiratory reserve volume. This is the maximal volume of air that is expelled from lungs after a normal expiration. Normally it's 1,200 milliliters, then it will decrease. Inspirational reserve volume is 3,000 milliliters and decreases, and this is basically the maximum amount of air that you can expire after a normal inspiration. And then there's vital capacity. This is 4,700 milliliters, and there's a slight decrease. And this is basically the greatest amount of air that can be expelled from the lungs after taking the deepest breath you can possibly do. Then there's residual volume. This is 1,200 milliliters, and this slightly decreases. And this is basically the amount of air left in the lungs after you breathe out the most you can. Then there's tidal volume, is 500 milliliters, and then it increases up to 2,000 milliliters after exercise. And this is basically the volume of air inspired or expired in your breath. Then there's an increase in tidal volume. This is the amount of air breathed in and out on each breath. Approximately, this is 500 centimeters cubed at rest. However, only 2/3 of this is used, which is 350. Only that much reaches the alveoli for gaseous exchange. And during exercise, tidal volume increases for more air to pass to the lungs. The volume of air passing through each minute is the minute volume, which is the breathing rate times the tidal volume. Tidal volume is elevated by aerobic and anaerobic exercise, and during exercise, oxygen depletion triggers a deeper tidal volume to compensate. And that's my presentation.